In this video, we build on the first normal form concepts from the previous video, and we introduce second normal form. We use more of our terminology, and we illustrate some examples. Second normal form builds on first normal form. In other words, a relation cannot be in 2NF unless it is already in 1NF. This is very important because if I ask you if a relation is in 2NF, or if I ask you if a relation is in 3NF, you have to backtrack and determine if the relation is in any of the earlier forms. So don't simply start looking for 2NF. Start looking for 1NF. If you meet 1NF, then start looking for 2NF, and so on. A 2NF relation meets all the requirements of 1NF, and here's our terminology, every non-key attribute is fully functionally dependent on all the candidate keys. So every column that is not part of a key is determined by all of the keys. If you're building your cheat sheet, add this to your cheat sheet that you started building in the previous presentation, and now you have a quick and dirty definition for 1NF and for 2NF. Here's a logical design. In this logical design, the relation is called fish data, or I added a T prefix because it will become a table. The attributes are fish, average weight, best lake, total caught, total pounds. The fish attribute is underlined, meaning it is the candidate key, which means it's the primary key because there's only one key. The non-key attributes, average weight, best lake, total caught, total pounds. The key attributes are fish. Is this in 1NF? It meets our requirements. There is a natural key, fish, and there are no duplicated columns. And the reason we know there are no duplicated columns is because all the columns have different names and none of them have subscripts. Remember, in our previous presentation we used a numeric subscript to indicate columns that contain the same type of data. Is this relation in 2NF? We can't say. We have to stop, throw up our hands, give up, find a new job, become a farmer, because we don't know. We haven't been given enough information to determine if this is in 2NF. And let me emphasize this point. You cannot look at the column headings and you cannot use those semantics to decide if this is in 2NF. Just don't do it. Here's the same relation with the determinants and the functional dependencies. Fish is the only determinant. Fish determines average weight. Fish determines best lake. Fish determines total caught. Fish determines total pounds. Flip back a couple slides. Every non-key attribute is fully functionally dependent on all the candidate keys. And we can see that that is true because every non-key attribute, average weight, best lake, total caught, total pounds, each one of those individually is functionally dependent on the only key, which is the candidate key. Therefore, this table is in 2NF. We're following rules. We're not using intuition. We're not using the semantics of the column names. We don't need any data. Is this table in 2NF? Yes. Again, it meets our requirement. Every non-key attribute is functionally dependent on all the candidate keys. Even though one of the columns is called distance to the moon, which seems to make no sense whatsoever for this relation, we have still defined a functional dependency where distance to the moon is dependent on the candidate key fish. It is in 2NF. You must fight the urge to use the column names. This relation is not in 2NF. We added another attribute, best-selling boat, in 2012. But look at the list of determinants, the list of functional dependencies, and you will see that best-selling boat in 2012 is not included anywhere in that set of functional dependencies. Therefore, the 2NF rule is violated, and there is a non-key attribute that is not fully functionally dependent on any of the candidate keys. Not in 2NF. Again, no data is necessary to figure this out. Data just gets in the way and causes problems. It can cause false positives. Don't look at the data. Well, we've determined something's not in 2NF. We run outside, we scream a little bit, we take a deep breath, we have a cup of coffee. How do we fix it? That is part of your job. Part of the assignments you will be given, part of the tests you will take, is fixing normalization problems, going from 1NF to 2NF to 3NF and so on. Another way to look at the problem is that normalization is attributes becoming relations. That's how we solve the problem. That's how we go from 1NF to 2NF. We take attributes out of the relation and make them into their own separate relations. And if you can tell me what all these pictures have in common, I will give you extra credit. You can email that to me. The way we fix it, the way we go from 1NF to 2NF, is to take out the non-dependent, non-prime attribute and put it in its own table. This makes sense because since that attribute was not dependent on any of the keys or all of the keys in the original relation, it doesn't make sense for it to be in that relation. Therefore, we make a brand new relation, we put that attribute in there all by itself, and we make that into the candidate key. You will have to make up a relation name for that, and you will have to create the new relation, and you will have to edit the original relation and remove that attribute that used to be in there. We end up with two relations, or two tables if you will. The second table has no determinants. I'm going to say it has no determinants. Mathematically it has one, but for our purposes there's no determinant because there's nothing for it to determine except itself. And there is your solution. Here is some data in that table that was broken. This is the table that had fish as its primary key, but it had the best-selling boat in 2012 attribute, which was not dependent on that primary key. We decided that this was not in 2NF. Just to illustrate why we're trying to get out of 1NF into 2NF is that we are trying to avoid what's called an anomaly. The anomalies come up here where we've got multiple values for that best-selling boat attribute in different rows in the table. So there's obviously a problem because you can't have 7 different best-selling attributes in the same table. There should only be one, but it's very easy to get 6 or 7 different values because we've got it stored 6 or 7 different times. It should not be stored in every row in that table. Another problem is if we delete every row in the table, we lose the value of best-selling boat even though we're deleting fish from the table. So an unrelated attribute can cause an update anomaly, and an unrelated attribute could accidentally be deleted when we're deleting rows from the table with the intention of removing some other kind of data. For now, I just want you to be able to tell me, and I want you to have a quick answer, that we normalize to prevent or avoid, actually, update anomalies and delete anomalies. Here's an example I like to spring on my classes. I would show you this, and I would ask you, is this table in 2NF? So if I see you at Chipotle and we're both standing in line waiting to get a burrito, I might show you this slide, because I carry the slides with me all the time. And I might say, is this table in 2NF? If you look at the graphic, hopefully you'll realize that this is a trap. I'm trying to fool you. The answer is, you don't know, because you don't have the functional dependencies and you don't have the determinants. I gave you the natural key right there, but I'm still not telling you if the natural key determines any of the other attributes. So you cannot give me an answer. You can't look at the data, because I could easily break this. I could create a false positive with the data. When you turn your head to order your burrito, I could add another row to the table, and I could break any dependency that you think you've inferred from the data. Do not use the data to decide dependencies and to decide determinants. Here's some practice for you. Without looking at the following slide, look at this slide first. It's in 1NF because it has a natural key, which in this case is A, the A attribute. And it's in 1NF because there are no columns containing the same type of data, because we have no subscripts. A, B, C, or B, C, D, and E are all different types of data. And then I'm giving you all the FDs and determinants. I'm telling you that's all of them. You don't have to guess, you don't have to worry. You will always be given all the FDs and determinants. A determines B, so given A, I know B in any row in the table. A determines C, A determines D. Hopefully from your intuition then you can notice that there is nothing determining E. E is left out in the cold. E has no functional dependency on any key in the table. E does not depend on A. The answer then is we are not in 2NF, we're in 1NF. And then you should take a moment, grab your notes, and figure out how to fix that problem. Remember what we did on a previous slide to solve a problem going from 1NF to 2NF. Think about what we did. Solve the problem here. I will go get a burrito while you solve this problem. I'll be right back. I'm back. Flip to the next slide. Here's another exercise for you to solve. In this case, I provided a relation with a primary key, A, but 3 of the columns contain the same type of data, B sub 1, B sub 2, B sub 3, and then there's C. I've given you all the functional dependencies and determinants. A determines B sub n, so A determines B sub 1, A determines B sub 2, A determines B sub 3, but nothing determines C. And you can tell then that we're not even in UNF, and since we're not even in UNF, we're not in 1NF, and since we're not in 1NF, we're certainly not in 2NF. So here's another exercise for you to solve. If you can solve these 2 slides, 12 and 13, and you can show your work and explain what you did, then you have successfully grasped the concepts illustrated in the first 3 presentations here.